So what we're going to be doing today is implicit differentiation. So here's the main difference if we're highlighting. I love highlighting. Explicit equation versus an implicit equation. One where you can write y all by itself would be an explicit equation. But in this second equation here, this implicit one, x squared plus y squared equals 16. And we used to learn these in the grade 12 curriculum, what that looks like and how to graph them. But we don't as much anymore. Do you know what that is? It's a circle. That equation right there is the equation for a circle with center 0, 0 and a radius of 4. Perfect. That would be what that equation actually shows. Now, unfortunately, you can't write this with y by itself in just one equation, because if I move the x squared over, and then if I wanted to get y by itself, well, whenever you square root, you have to do plus or minus, so that technically means there's two explicit equations, one that would be positive and one that would be negative. The circle is not a function. Does that make sense? Because it doesn't pass the vertical line test. So right now this isn't a function, but when I split it up into these two explicit equations, if I make this one yellow on the graph, that would represent that part of our circle. And that yellow part by itself is a function. And this one, if I were to graph this one, that would be that part of the circle. So the green part by itself would be a function, but the two together would not be. Now, despite that, we can still find the derivative of a relation like a circle with something called implicit differentiation. So even though we have a circle, we could pick any point on this circle and still figure out what the slope of the tangent would be at that point. So here we have that same equation, and we're going to use implicit differentiation to find dy dx. First of all, we use the idea that there is a relationship between y and x, and just like we solved here before and said what the relationship is between y and x, y is equal to plus or minus the square root of 16 minus x squared. And when I look at both of those, can you see that you could do the derivative of those? Right? You'd have to change the square root to a half and then use the chain rule, but you could do the derivative of those. So the way that implicit differentiation works looks like this. We take the derivative, if I want to find the derivative of dy dx, I take the derivative of my entire equation. I take the derivative of the left side, and I take the derivative of the right side. So I'm going to take the derivative of this side, and I'm going to take the derivative of this side. This will be a step that you won't necessarily show from now on. I'll highlight the step that you'll probably start on, but for this being the first one, we'll look at each little thing part by part. Okay? Now, when you're taking the derivative of x squared plus y squared, from our rules before, that means you have to take the derivative of x squared, Because we had a rule saying if you're adding functions, you can take the derivative of each one separately, right? Plus, we're going to take the derivative of y squared. And we may as well do this one right away. What's the derivative of 16? 0. A lot of this is easy. What's the derivative of x squared? 2x. So that part is going to be straightforward. Now, what's the derivative of y squared? That part, well, right here it's saying the derivative with respect to x of y squared. There's no x in there. We could take the derivative with respect to y, but we couldn't take the derivative with respect to x because there is no x there. However, we saw before that you could get a relationship for y. Y is a relationship in terms of x. And if we wanted to, we could take the derivative of both of those if we had to. So what we're going to do in this case is we're going to imagine that this y is something with x's. Okay? I'm going to do that. I think it helps you see it if we use our imagination and actually write something with x squared. Okay? That's what I want you to imagine. If you had to do the derivative of something inside, maybe it's an x cubed plus 5x inside. Maybe it's x squared minus 7x inside. So let's even though it's not true, let's pick something specific. If you had that inside and you had to do the derivative, what would you do? Chain rule. And the chain rule would say, take the 2 out in front, right? Subtract 1 from the exponent, and then do the derivative of the inside. Okay? Which would be 2x minus 5 in this case. Okay, but we don't know what's here. We just know it has an x. So we still wouldn't know what's here. We just know that it has an x. And here would be the derivative of what's inside. Okay? Now the interesting thing about what's inside is just y. The derivative of what's inside will just be dy dx. Because that's the derivative of y. That's what the derivative of y means. It's just dy dx. So now when we look at our equation, I'll turn back to green, we're going to think of this y squared as a chain rule. How does the chain rule work? You would bring the 2 out in front, keep the y the same, subtract 1 from the exponent, and you'd get 2y to the 1, which is just 2y, times by the derivative of the inside. And what's the derivative of y? dy dx. And it's still equal to 0. I'm going to put a star by this line because most likely you are going to go from here to here when you're showing your work. Because you're going to take the derivative of each thing separately. The derivative of x squared is going to be easy. The derivative of 16 is 0 is going to be easy. And then the derivative of y squared, you're going to think of it as y is a function or a relation of x. And because of that, you can do the chain rule first, and then the derivative of y will just be dy dx. So solving for this, if I wanted to get dy dx by itself, I could just subtract 2x on both sides, and then divide both sides by 2y. And we have the derivative in terms of y and in terms of x. And if we look back at our circle, okay, let's say, I don't know, what point does it look like I have there? It looks like at 45 degrees. But let's say my x coordinate is 2. That would make my y coordinate square root of 12. Does that make sense? My x coordinate's 2. My y coordinate would be square root of 12, so that x squared plus y squared would still equal 16. Okay? For this equation, you need an x and a y to find the slope of this line, because if I just used x, I wouldn't be able to tell if I was talking about this point where x is 2 or this point where x is 2. So I need an x and a y in my derivative in order to be really specific about which point I'm talking about. So I could plug it in when x is 2 and y is root 12. This example would say the slope of that line is negative 4 over 2 root 12. And that, of course, could simplify. But that would be the basic idea of finding the slope of that line at that point. This is really simple for finding the derivative compared to if you had to substitute in to figure out the derivative. In fact, even our explicit equations, if we go back to our previous screen here, even our explicit equations we could have done this way. Okay? If we take y equals 3x squared minus 2, and we took d dx of everything. If we first think of just y, what's the derivative of just y? It would be 1. And then he did the chain rule. What's the derivative of the inside? dy dx equals 6x. That's using this idea to stuff that we've done before. Of course, the stuff that we've done before, we just went dy dx and then did the derivative of the right side. But technically, if you did the derivative of y, and you think of it first as chain rule, while just having a regular function, that would just be 1. Derivative of the inside would be its derivative, dy dx.